بسم الله الرحمن الرحيم قال رب اشرح لي صدري ويسر لي أمري واحلل عقدة من لساني يفقهوا قولي. In the name of Allah, the most beneficent, most merciful. Today is my lecture on stress and strains in flexible pavement. So, before we move on to stress and strain in flexible pavement, let's let's define the basics. Let's recapture what you know about stress. Stress is force per unit area. The load per unit area. Its units are megapascal, pound per square inch, and kilopound per square inch. It can be of a different type. It can be a bearing stress, it can be shearing stress, and it can be an axial stress. When we talk about strain is the change in length per unit length, and it's a dimensionless entity. Another word you will use is the stiffness, or we call a Young modulus. It is the ratio between stress and strain. And this, what we are talking here, is about a one-dimensional strain stress. Talking about one-dimensional stress. So, if you are talking about an elastic material, it's a modulus of elasticity, or elastic modulus, or Young modulus, whatever you say. So, another terminology you are going to learn is, now let's define this stress and strain. For example, if a material is subjected to load, continuous load or compressive load, as you can see, the point where stress is proportional to strain, directly proportional, or the linear part of this behavior is called elastic range. And then it comes to other ranges such as elastic and the plastic range. And this is the ultimate point of the material when it gets broken. As you can see, another terminology is the Poisson ratio. This, I mean, if I compress the material in this unidirectional, there will, or you can see if you're talking about 2D material, 2D analysis, it means if you are pushing it, compressing it in Y direction, there will be always, there also be a change that will take place in the X direction. So what we say, what is the Poisson ratio? It is the ratio, the change in Y direction to the resulting change in the X direction. Remember, this has taken place because the material is being compressed in the Y direction, and as a result, there will be a deformation, or there will be change in length in the X direction as a result of applying loading on the Y direction. So typically, it can be expressed as mu or nu, and it is, as I said, ratio of stress strain in Y direction to the ratio of strain in X direction. When we talk about pavements material, the value is between 0.15 to 0.50. And when we talk about unbound basis, it is 0.30 to 0.5. And for subgrade, it is between 0.1 to 0.5. In the case of Portland cement, it is 0.15. Other materials, the Typical value of elasticity modulus is a rubber 1000, wood 1000 to 2 million, aluminium 10 million, steel 30 million, and the diamond is 170 million. Yes. Typical modulus values, hot mix asphalt 450, Portland cement 4000, aggregate treated base, asphalt treated base 150, cement treated base 700, in concrete 1500, granular base 30, granular soil 15, and fine grade soil 4. Typical values of asphalt values dependent on the temperature. Asphalt 2 million at 32 degree Fahrenheit and 120 it becomes 20,000. Now, another thing that you are going to learn or going to see in your literature related to stresses in flexible pavement is the deflection. Deflection is just a change in length as compared to strain. Strain is the ratio of two length, change in length to the original length, but deflection is the only change in length. Its units are millimeters and mils. That means 0.001 of inch is mils, because the deflections are not in meters. Deflectors are in very low values and should be in low values. Otherwise, the pavement would have failed. So that's why we express mils, though 1 mil is 0.001 inch. Now, if you look at the system of how pavement behave, we already have discussed this many a times. Let's discuss it once more. That how the stresses and strains are created in flexible pavement and the rigid pavement. In the flexible pavement, there is stresses are taken care by layer by layer. This asphalt concrete takes most of the stresses. Then it transfers to the base and subsequently to the subgrade. So there is a layer system behavior. And what I mean is all layer has to carry part of the load. While we talk about the response of PCC, means there is a slab action in which the PCC slab takes all the load and it seldom transfers the load to the subgrade. Now, when we talk about the how to analyze a system of flexible pavement, what we need to know or understand the stress strain behavior within the pavement structure related to the failure, that is cracking and rutting. In numerically, we compute deflections and strain, and we know that different models have been developed with time. They have some capabilities, they have some assumptions, their complexity varies, and the material information is always the requirement. In an ideal model, it predicts stresses, that is based on static and dynamic load, and strains based on material properties, traffic, and environment. Different method has been developed. The famous being is the multi-layer elastic theory, finite element method. Then there is a viscoelastic theory, means time and temperature dependent behavior, dynamic analysis, inertial effects, and thermal modulus, that is the response with respect to the change. They are the most widely used, they have a reasonable results, and their properties are relatively simple to. When we talk about the flexible pavement, let's assume a truck on a pavement. So whenever the truck moves, it applies or it results in this deflection, and slowly but gradually as the trucks move forward, this the stress or deflection here subsidize. So we use this method in knowing the elasticity modulus, especially uh, for a flexible pavement. And this is one example how we do it. And actually, this is a falling weight deflectometer concept, in which from using the geophones, the dropping weight and deflection basin, we get the deflection, then they are reported, and the stresses and strain measured, and the resultant elasticity modulus is obtained. So when we analyze pavement, we have different theories. One is multi-layer elastic theory, in which the pavement is assumed to have different layers, and a load, a tire load is applied, and there is a contact radius, and this load, this, this area, this radius depends not only upon this tire pressure but upon the load as well. And that's there we can find stress at any point within the pavement, whether it be point A or point B, or maybe point directly below at the surface, or anywhere uh, at any layer. Whenever we do this, we always have to know that there is each layer that is continuous, homogeneous, they are only continuous, they are same at any point, they are isotropic, the materials are linear elastic. We don't consider the material, the weight, and every material has its own thickness except the substrate that has got infrared. So when we calculate the stresses, we know that we calculate the surface stresses because of the circular load, vertical stresses, and uniformly distributed. We assume that there is a full friction exists between two layers, and each layers are continuously submerged. So let's once again have this review that in the flexible pavement stress, we calculate stress, strain, and deflections. Stress we report in PSI, strain in microstrain, and deflections in mils. Over the years, there have been different theories, and based on different theories, the stress can be calculated. First thing is the first theory is called elastic half space, in which we say no pavement exists, and the load, the pavement load, the load from the tire directly transferred to the ground. And this stress at this point, at this depth Z, can be calculated using this equation. It's below the point, over pi 1 divided by the ratio of the point away from the center, that is R, to the depth, that is R constant. So if the point is here, it means it is R distance from the center of the load, and you are interested in knowing the load at stress at this point at depth C. This load, this stress will also be calculated at this point. At this distance, R will be 0. So consequently, R over Z will also be 0, and you calculate the point directly with sigma Z. You can see that if you have this R as 0, so that means the stress at this point will be simply 3 over 2 pi P over Z square, where sigma Z is vertical stress, Z is the depth, and P is the point load. Now, this theory can, this stresses can also be calculated either from the equation or by using Foster and Allen solution. Now, what we have done is that we have imagined that whatever the load, this point load, the equivalent stress bulb will be circular in nature. The contact area will be circular, that has a radius A. So a whole tire will have a 2A radius, 2A radius, or it will be diameter 2A. And if you get the slice out of that load, circular load, you can calculate stresses, vertical stresses in this direction, tangential stresses, and the radial stresses. And last but not least is the shear stress, that is on all the face TR, Z. Whatever result is not there, but a deflection will also be there because of this load having a tire pressure of. So using this, we can calculate the stress at any of these points, at depth 1A, depth 2A, point 1A from the center of the load, or point 3A on right side of the load. You can calculate on the left side at this point, or any point between here or wherever at any depth you desire. There are equations that you can solve, and this has been applied, and you can use these equations for vertical stress, E over 2 pi Z R over Z square. If you are interested in knowing the radial stress, you can use this equation. Tangential stress, you can use this equation, and here mu represent what? Mu represent the Poisson ratio, between, that is the ratio between strain in y direction to the strain in x direction. You can also calculate the tangential stress. Now, the strains you calculate at if at r is equal to 0. So vertical strain will be 1 over E sigma Z minus mu times sigma R plus T, and obviously you must be knowing that strain in each direction will be calculated in this manner, that in which the, the main strain will be because of sigma r over E, while the negative impact will form sigma z and sigma t. So the strain in other direction, stress in its other direction will actually reduce the magnitude of radial stress in that particular direction. And this is what? It's a bulk modulus, and it is dependent upon TZR over G. And you know what is G. Now, if you assume that the stress is calculated directly below the point, that's obviously R will be 0. So, all those equations, if you put R equal to 0, then you will calculate sigma z, sigma R, and Tz. Similarly, at R is equal to 0, you will calculate strain in Z direction and calculate strain in radial strain. Again, all the things are known to you. A is the contact pressure, Z is the depth, mu is the Poisson ratio. And to calculate vertical deflection, you will use this equation. And if you put Poisson ratio as 0.5, this whole Tesla equation will, reduce to this equation 3q times a square 2e a square plus z square, where q is the tire pressure, a is the contact. Uh, as you can see, using these equations are sometimes very tedious. So, Foster and Allen in 1954 has developed simple charts so that you can calculate the stresses directly using this chart. So, if you look at this chart, the charts have different parameters. On x-axis, it reads stress over Q into 100. Y-axis, you have Z over E. And there are curves, and these curves are based on R over. So let's see that chart. This is how the chart for calculation of vertical stress is presented. Again, this is what? This is Z over A. And this is stress you calculate, and this is R over A, as I was explaining here. The number on the curve is R over A. R over A means how much the point is away from the center of the load, and Z upon A is the ratio of the depth of the layer to the contact radius of the tire. So Z upon A can be 0, RA upon A can be 0. But if Z upon A is 0, then obviously the stress will be maximum. As you know, this is a flexible pavement, and as we go below, this stress will tend to reduce. Foster and Alvin have also presented the chart for calculating tangential stress, and here this is depth over radii, and then here this is stress, and this again R over A. All the numbers are R over A of the curves. Shear stress can be calculated from this chart. Similarly, vertical deflection, you can use this chart for calculating. So whatever is the value here, you input P, A, actually you get this F value. So once you get F value, you always know your tire pressure, you always know the contact radius, and you know the elasticity modulus you can calculate the deflection. So let's see how to do it. If that is the there is a there is a point, this point away 6 inches away from the center of the impact load, and we are knowing this, want to know, we are interested to know the stress at this point. So for a given, we have been given that there is a load on the tire that is 9,000 pound. This is the load from the tire. Pressure is, I mean the tire pressure, it is 80 psi. And our objective is to know the vertical stresses 6 inch away from the center. That is Z is equal to 6 and R is equal to 6. 6 inch away from the center is R and 6 inch below from the center is Z. So first we want to know what is the contact radius. We always know that the tire pressure is force upon unit area. So that's why we know this force, this is 9,000. Area is pi a square. Remember, don't get confused between R and A here. All these stresses, all this pressure, take A as the contact radius, and R is the radial distance from the point of the contact. So actually, this area of the contact of the tire is pi a square, or you can say pi into radius of the contact. So using simple mathematics, for A is equal to 6 inches square. So if order to know to read the chart, we need two values, that is Z upon A and R upon A. Z is given to us 6 inches. A we have calculated as 6 inches as well. So Z upon A becomes 1. Similarly, the point is 6 inches away. That's R is 6, A is 6. So Z upon A and R upon A both becomes 1. Now, using these values, we can calculate very simply. So we had Z upon A is 1, so we'll keep moving horizontally at Z upon A 1, and we try to find, want to try to know which curve has R upon A as 1, because our R upon A is 1. So once we find it, we stop over here, and once we stop, we go perpendicular to this point from this curve, and you find that this value, that is sigma Z over Q into 100, here it's more than 30. Now, it can be 33, but can be 32. And it's debatable. It's obvious. It's an approximate solution. And the easiest way for you to approximate is that we can always know that this point is not at the center. So if it is not the center, so that's why we can safely assume this value that we are want to know falls between 30 to 35. But it's not 40. So it's between 30 to 35. And if it is between 30 to 35, the simple thing is we can take the average. So 30 and 35, it makes 32.5. And for the sake of approximation, take as 33. So sigma Z, you know that this value is equal to 33. Sigma Z over Q multiplied by 100 is 33. You know Q, 80, and with simple mathematics, you could know the vertical stress at point 6 inch away, at 6 inch depth on load of for a load of 10,000 pounds on pavement, on the, or you can say on the surface of the substrate here. Uh, when you want to do the when you want to calculate the deflection, as you can have two types of deflection, depends upon the type of the material. If you have a rubber tire, then the deflection is simply will be W naught 1.5 times Q times A over E. E is the elasticity modulus, obviously, of flexible rubber. Q is a tire pressure and A is a contact radius. And if you would have been using a steel tire, then obviously the impact of the steel tire will be different. And you can always know that this reflection for a steel plate will be more as compared to the, it will be less as compared to the rigid plate. So the rigid plate is actually 79% of the deflection of the flexible. So if you are using this rubber or you're using this steel as a, so that is if the material is different. Another way, if the response is you are calculating on rubber, it will be different as compared to the steel. It can be no. What I am saying here, this doesn't apply for steel tire. I am saying here that if you have a tire that has a flexible of rubber and it is based on rubber, obviously deflection will be less. And if there is a tire and it is uh, supported, the tire is being loaded on a steel plate, the deflection will be different. So that's why the type of the pavement will have a different responses. Now, if you have been giving multi-layer system and we want to know the deflection at point A using this one layer theory, we can do it like this. Though there are methods that are available for calculating the flexible stresses in multi-layer system. So let's assume that we are not using it, and for us this Z is 12 plus 8 plus 4, that is 24 meters. So if my subsurface is the clay, then the deflection will be 71 mils. And if my subgrade is sand, this deflection will be 7.1 mils. So obviously, this is higher deflection as compared to the lower deflection because of the high elasticity modulus of the sand. So the point is, the magnitude of the deflection depends on the surface on which you are applying the load and at the subgrade. Obviously, if you have a clay, your deflection will be more, and if you have a subgrade as dense sand, then it will be, the deflection will be higher in clay as compared to the deflection in the sand. So, in a nutshell, the stress is dependent on two things: the type of the pavement, whether it's a flexible plate or a rigid plate, or it also depends upon the type of the support. So if you have a clay as your support, then and then obviously the deflection will be higher, and if you have sand, then the deflection will be lower. So this is how deflection is calculated. Just Z upon A and get this curve. Uh, Obviously, at the previous example, that was 24, 6, R over A is 0 because the point was directly above. So we can find F. And once you find F, you know Q, you know the contact radius, and you know the last support. That's how you calculate these values from the, uh, from, for this data. Now let's see if you are talking about a multi-layer system. We always know why is there is a pavement. The pavement is to protect the subgrade, reduce stresses to tolerable level, to prevent excessive settlement or collapse. The vertical stresses that is calculated on the top of the subgrade important for working, and there these allowable stresses are dependent on the E of the subgrade material that we have explained. And if you want to know the combined effect, calculate the vertical strain. It is generally assumed that the stresses in radial and tangential directions are of very little values. So that's why we tend to ignore the these these parameters, these inputs, while we calculate the vertical strain. That's why vertical strain is sigma z over E. Though mathematically it is not like this. It is also mathematically it depends on stress in radial direction and stress in tangential direction, and we, we basic equation is this. But for assumptions, we only calculate sigma z upon E because this is the maximum factor. This will have a subtractive effect. So even if you just neglect it, we will be getting more strain, uh, and that is acceptable. Then, if you're talking about the horizontal tensile strain, we calculate right at the bottom of the flexible layer. So, and this is for fatigue cracking criteria. So it also depends on overall minor principal strain and horizontal principal strain, though it's not an actual principal strain. When we talk about the overall principal strain, obviously we are talking about sigma z, x, y, z, tau x, y, tau x, z, and tau y, z. We calculate, use cubic equation, stress tensor, sigma 1, sigma 2, and 3, and you can calculate the sigma T3 as 1 upon E, sigma 3 minus B, sigma 1 plus sigma 2. The horizontal principal strain, you can use this more cyclical equation as this always is the basic course you have as a civil engineer. You had this course and you know this equation from the previous knowledge. And this again is a shear strain, Ex and Ey, and you can calculate this tangential horizontal strain at the bottom of the S40. Nowadays we have program called CAN-PAVE or CAN layer that can predict a failure, and it is using the same equation. And if you assume that there are two layers in the system, one pavement is considered as one layer, and the subgrade is considered as second, that will be called a two-layer system. it is also it is derived. It is actually these assumptions, these calculations are based on the model presented by the system. So you can always calculate the vertical deflections and the vertical stresses. And these values are dependent on the stiffness ratio E1 and E2. The graph is presented from there, and then you can always find this. So there are assumptions in which one layer theory that all layers can be represented as one. Sigma surface is sigma top of the surface. But for a two-layer theory, vertical surface deflection and vertical interface deflections are different. So for flexible pavement, this is 1.5 QA times E2 and F2. This F2 is calculated from the chart. E2 is the modulus of the subplate. And for the rigid plate, only this coefficient has changed. Let's see if you are interested in knowing the surface deflection. Surface deflection means the point directly at the contact of the tire and the pavement. Like you can see this cross here. So if you are interested in knowing this deflection over here, this is called a surface deflection, in which you know what you do. This curve are E1 over E2 curve, and here you have what? You have H1 over A. So, and if you know H1 over A, and you know E1 over E2, you can always find this F. In this example, we have H1 is 6, A is 6, so H1 upon A is 1. And then E1 is 50, E2 is 10, so this 5. So just go perpendicular, just set and get this. You can always find this value of maximum deflection. And for surface deflection, again, you will use this H over A as 6 over 6 is 1, R is equal to 0, and E1 over E2 as 5. So you get this value as 0. Remember, we have different chart for calculating the surface and interface deflection. We use this chart for this. Interface deflection, I mean here. Surface deflection, I mean this much. Now, if you compare surfaces versus interface deflection, you'll see that at the top layer it is 7% and the subplate is 93%. And if logically, if you see, there are no much difference between the surface and interface deflection. They are around the same. If one is interested in knowing the vertical stresses, he or she can use this graph. And again, you want to know is A over H1. You need A over H1. and go like this. Just set your modulus and you will always get this value. However, in this example, we have been given, we are just in knowing H1. So what we need to know, but since sigma C is already given as to us as 8 psi, so we calculate sigma C over Q, that is 8 over 80, that's 0.1. And calculate, we also want to know this modular ratio E1 over E2, and that's 500,000 over 5,000, that becomes 100. And we go this figure, we go perpendicular to point 1, intersect at 100, and you get A over H1 value. And since A is known to us, you can always know how this H1, what should be the value of H1 to keep the stress in the clay as 8 psi. Now, if you want to know the critical tensile strength at the bottom of the separate layer, you can use this charts. Remember, there is a way to read this chart. The curve going from left to right is the modulus ratio, E1 over E2. The curve that are going from bottom to top represents H1 over A. So what you need to know is you want to know E1 and E2, and you want to know H1 over A. Once you get this intersection value, you can find this strain factor. And once the strain factor is you can use this relation Q over E1 times Fe to calculate the correct critical strain. Let's try to solve the given example. We have been given a contact radius of 6 inches, tire pressure 80 psi, E1 200,000 psi, E2 10,000 psi. So, and we are interested in knowing this strain. And obviously, we're going to use this chart. First, we will calculate E1, E2, 20, and then we calculate H1 over A, 1. So how you are going to do this? So what you do, you can use start from either from left to right or right to left, bottom to top, it won't matter. For example, if I want to start it like I will follow this curve of 1 till it intersects my desired ratio. This is 2, I am not interested. If I go up, this E1 over A2 is 5. Obviously, my E1 over A2 is 20. So I will follow this curve right this point, and here I find that E1 and E2 intersect by H1 over A is 1. So this is a cross, and this is my intersecting point. Once I know the intersecting point, and I'll go perpendicular and find this value. Again, it's not 1, it's not 2, but actually it is not 1.5 either. So any value between 1 and 1.5 will be this Fe. Let's assume this 1.2. Again, my methodology, just take average. For my average, 1.5 and 1, it will be 1.25. But for the sake of calculation, take this as 1.2. So find the value of Fe, both Q, O your E, that is 200,000. Remember, we will not take E is this because conceptually tensile strain is calculated at the bottom of the layer of asphalt layer, and the value of like for calculating the strain, the value of elasticity modulus of asphalt concrete will be used. So now we find the value of tensile strain. It's very important in the context of the plane. Let's move on to a three-layer system. Obviously, this first one is an asphalt layer. The second one is an aggregate-based layer, and the third one is the separate. Each one of them, wherever different, those are the shown. And you can calculate sigma at this interface, at this surface, and all the values of stress or inlet. So all these stresses will depend upon the ratios K1, K2, A, and H. Uh, Jones has developed a chart to calculate these values, and once you know this value, you can find the relevant stresses. This is a Jones table in which you know H, you know K2, you know A, and you can simply plug in the value and you will find this value of ZZ1, ZZ2, ZZ1, RR1, ZZ2 for different values of K1, K2, and K. But if your values are in between, then you have to interpolate linear. So once you know the values from uh, your chart, you plug in this value and use this relation to calculate stresses in Z1, Z2, radial stresses, and then the strain as you decide. Nowadays, there are different software that can be used to instead of Jones table, obviously. So we use those software to calculate the stresses to for uh, if you want to know how this software are used, please visit my YouTube channel video as displayed on slide over here, or you just can type ADNAN QADIR LED, or you can just search CanPave software, example of CanPave software, and how the software can be used. So that's it. Thank you very much for this long lecture. Uh, Inshallah, we'll see you once we do that. Till then, Allah.